Hi, and welcome back. This is the first of two videos for Chapter 6. Now, Chapter 6 introduces us to a tool called Gauss's Law, which is a natural consequence of fields in conjunction with something called flux. So, what I'm going to start off with today is a conversation about um, something called flux. And to do that, I need to have a conversation about surfaces and geometry. So, what you're looking at here are two of what we would call, from a math standpoint, closed surfaces. Whoop. Now, by closed, what I mean is that this cube, for example, and this sphere right here, don't have any holes in it. If I were to carve a hole, for example, here, this surface wouldn't be considered closed anymore because it would have a hole in it. Now, that said, um, mathematically, when we talk about surfaces, we can talk about the direction of out and in. For example, let's pretend that you had I don't know a charge on the inside of this. For example, maybe it's a proton has a value of positive e for its charge, and I was looking at the electric field as it left. So here, as you can see, when the electric field leaves, if I were to look at the surface and its orientation with respect to the electric field, the field is exiting this way, and this forms what we would call the outside of our cube, and this would be the direction of out for the surface. So this electric field would be traveling outwards. Likewise, if I were to make this, instead of a positive charge, a negative charge, we know from our discussion about electric fields that the directions of the arrows would be inwards instead of out. So you would have field going in like that, which is opposite the direction of out for our surface. So, because of arguments like this, what we do is we typically define something called the surface normal. Now, the surface normal is based off of the direction of out for your surface and basically the area. So, we might call it, for example, S. It would be a vector. Its magnitude would be the actual area of your surface. And we would create a little unit vector, which we usually call n hat, and that's the direction of out. Now, in this case, what we have is we have a field that's either exiting or entering some sort of surface right here. And field that goes through a surface, let's pretend this is a surface right here, it's going through it, you can characterize with something called flux. Okay, flux is basically how much of a field that directly goes through, any given surface. So, as an example here, if I were to just sort of draw some sort of arbitrary squiggly looking thing like this, this is my surface right here. This is not a closed surface. This is just one side. Okay. And if I were to sort of draw a field entering here, and then exiting this way, like that, going through it. The way we would define our flux around this would be how much of this field actually makes its way through the surface times the area of the surface. So there are two different ways you can define this, and I'm going to talk about why the definitions look the way that they do here in a moment. So we use capital phi for Flux here, the sub E means for the electric field because you can do it for magnetic fields or any other field that you're dealing with. And if you're dealing with a constant electric field in a constant area, then this is just E dot the surface normal. Okay? So why is it this? Well, all right. What I'd like you to do is to think of this right here, but we're going to turn it on its side. So here I am looking at this as a side view. So what I've done is to rotate it like this. I'm just seeing the side of my surface here. And, maybe these are my little electric fields that are coming in like this. Okay. So the direction of out for me, or at least for the surface here, would be like this right here. So this would be the direction of out. This would be my surface normal. Now, so if you look at these vectors right here, and you think of using the side of the surface right here as sort of like the y-axis. And then what we'll do is we'll create an x-axis that looks like this. So here's our x-axis. Then what you can do is you can use the tools that we learned back in University of Physics 1, and you could break this up into components. It would have an x part, which would be this part right here, and then it would have a y part, which would be this part right here. And the x part right here is what makes its way through. The y part actually rides along the length of the surface, but never actually makes its way out. Now, if you think of that in terms of say, in relation to the direction of out for our surface, in the direction of the surface normal, and we call this angle right here theta, then this part right here, the x part, is cosine. So in terms of an electric field, it's the cosine part of the field relative to the surface normal that makes its way out. E cosine theta is the part that makes its way out. S is the magnitude of my surface. That's how big it is. And we know from, dot products and things like that, that's really just what this is. Now, what do you, if you have an electric field that isn't constant, or what if you have a surface that is changing somehow? Well, what you do is you promote this to an integral, and you integrate over the surface. So another way of writing this would be the integral of E dot ds. Okay. Now, sometimes they also write this the following way, noting the fact that you have this relationship right here. E dot n hat ds. And this is, of course, over the surface that we're looking at. This is the way I'm going to write it in this class. Okay, but just be aware that if you were to, for example, look in a different book for reference or something like that, that you may see it written this way too. Or they may use A instead of S for the surface, A being area. They call it dA. So, like I said, this is the definition of electric flux. You can do that not just for the electric field, but later on we're going to be doing it for the magnetic field. Any sort of field, you can define flux. It's basically how much of something goes through an area. So, again, for constants, it's this. For things that change, potentially, it's this. Okay. So let's just do an example or two dealing with this right here. And so what we have here is a 150, and that shouldn't be newtons per meter. Let me fix that real quick. Can't do it that way. This should be per coulomb. Not sure how that mistake got its way in there. But 150 newton per coulomb electric field passes through a surface that has an area of 1 square meter. If the field makes an angle of 20 degrees with respect to the surface normal, what is the electric flux through the surface? So what I'm going to do is to, again, sort of look at this from a side view standpoint. So here's the side of my area, which again, my surface here is 1 square meter. That's its area. Okay. The direction of out, we'll call this right here. You could call it the other way. Really doesn't matter because when you look at the angle in between, it ends up being the same. So this right here would be the direction of in hat, right there. And, you know, maybe this is my electric field or a little bit of the electric field that's making its way through, like that. So what I'm given is that my angle here, theta, is 20 degrees. And I also know how strong my electric field is. In magnitude, it is 150 newtons per coulomb. So I'm given the area is 1 square meter. My electric field is 150 newtons per coulomb, and that my angle is 20 degrees. And I'd like to try to find the electric flux. Okay. Well, E is constant, S is constant, which means that the version of my equation that I can use is this one right here, which would again be, E dot n hat times the surface. And, it's 20 degrees right there. So it's just, E times S times cosine of 20 degrees. So if I plug stuff in, E is 150 newtons per coulomb. The surface is 1 square meter. And I have a cosine of 20 degrees here. Let me grab a calculator here. All right, let's see. That is 150 times 1 times cosine of 20. And I get 140.95. Now, if you look at the units are Newton meter squares per coulomb. There really is no unit of the electric flux. Later on, we talk about magnetism. There is a unit for the magnetic flux. It's called the Weber. Now, if I look here, I see 1 sig fig, I see 2 sig figs, I see 1 sig fig. So this ends up being somewhere around, 100 Newton meter squares per coulomb. Okay, so pretty easy. Now, from a more complicated standpoint, we have this one right here. So here I have a square surface that lies in the xy plane with sides of length 2.0 meters. So let me draw a three-dimensional coordinate system here, like this. This is z, this is y, this is x. Here we have a square that lies in the xy plane. The sides are length 2.0 meters, so maybe I'll draw my square like this. Okay, so this is my little square. I'll kind of give a little bit of a little texture to show that it's an area like that. And, this right here is the direction of out. Whoops, let me fix that. This is the direction of out from my surface right here. So it's right up the z-axis. Okay, so this has a length of 2.0 meters. This has a length of 2.0 meters. And I have this electric field that has a magnitude of 225 newtons per coulomb at the surface, but it has this form right here. Okay, so what we're given here is E naught. All right, so let me draw my electric field it's going straight up the x-axis, or the z-axis rather. So it's going straight up like this. So here's my electric field. It has the form of E naught times sine of k times x, z hat, going straight up z. So what I've been given here is sides of length 2.0 meters. I have been given that my E naught, the magnitude of my field, is 225 newtons per coulomb. I've also been given the value of K, which is 1 over 2.0 meters. And what I'd like to find here is the electric flux. Now, this is an example in which you cannot just assume that your electric field is constant or that your area is constant. And in this case, our area is constant, but our field definitely is not. Which means, unfortunately, that we have to use the version of electric flux that looks like this. It is the integral of our electric field dotted with the normal integrated over the surface that it passes through. Okay. Now here, we're dealing with Cartesian coordinates, which is pretty easy to deal with. Surfaces in Cartesian coordinates, when they lie in the xy plane, our surface element here is dx dy. Okay, you move along x, you move along y. That's how you make your area. Okay. Now, the dot product between E and N, this is N hat. The angle here is 0 degrees, and cosine of 0 is 1, which means that our integral really is just E ds integrated over our area. Now, our area starts at 0 on the x-axis and ends at L. Actually, that's along y, sorry. 0 on y and ends at L. It starts at 0 at x, it ends at L. So the limits of our integral are from 0 to L and 0 to L. Now, our electric field looks like E naught sine of k times x. We're integrating this with respect to x and also with respect to y. Now, if you look at my mathematical function here, E is a constant. This E naught comes right out. It's just a constant. That's 225 newtons per coulomb. I'll also notice that this function right here only depends upon x. It doesn't depend upon y. And what that means is that I can pull the E out, or the E naught out rather, and I can also integrate the y part separately. I can pull it out as well. What I can't pull out is the x part. Okay, so the integral of dy from 0 to L is super easy to do. That's just y evaluated from 0 to L, which is just L. All right, so this part right here is just L. This one right here is a little more complicated. For example, if we want to do this, let's do a change of variable first. I'm going to call u k times x. So du is k times dx, or dx is the same thing as du over k. Now, when I do that, what that does is it change my limits of integration. At the bottom, if I plug in 0 into x, that means that u is still 0 there on the bottom. Here, if I plug in L into x, this is k times L. So that's my upper limit of integration. It's changed. So now I'm just integrating sine of u, du. Dx is the same thing as u over k, so I have to pull a k out, 1 over k out there. Okay. And, the derivative of sine is cosine. The integral of sine is minus cosine. So you have a minus sign that sits out in front, a 1 over k, a cosine of u evaluated from 0 to k sub l. So let's plug that in. We have cosine of k times l minus cosine of 0. And cosine of 0 is 1. So that's what this is right here. That's this. So altogether, the equation for my electric flux is going to look like E naught, that's the first part, that's what's out in front, L, that's this, times minus 1 over k cosine of kl minus 1. So what I'm going to do here is to move this minus sign through here. It flips this. I have E naught L over K. And then I have 1 minus cosine of K times L. Now, so let's plug stuff in. E naught is 225 newtons per coulomb. The length is 2.0 meters. K is 1 over 2.0 meters, if you remember, comes from there. 1 minus cosine of 1 over 2.0 meters times 2.0 meters. So that's just cosine of 1. So let me plug the stuff in here. Put my calculator. 225 times 2. That 1 over 2 brings the 2 up to the top. Then times 1 minus cosine of 1. And I get 0.137 Newton meter squared per coulomb. Now, if I look here, I have 2 sig figs, I have 3 sig figs, I have 2 sig figs. So at the end of the day, I have 2 sig figs, which means that my electric flux here is really 0.14 Newton meters squared per coulombs. Okay, so not too bad. Maybe the weird thing here is the fact that you have to integrate it over an area, but you can see why, because you're adding up the electric field over it, and the electric field changes with respect to x. Okay. So let's talk more now about what the real power of this particular equation is, what this flux really is used for. So there's a mathematical law. You would learn it typically in Calculus 3. It's unfortunately a little bit above the pay grade of this particular class in order to derive it. And it's called Gauss's law. Now, Gauss's law relates the properties of a volume to the properties of the surface. Okay. The version of it that we're interested in is this one right here. E dot n hat ds. Well, that really looks familiar. In fact, I could have sworn like we used it here, didn't we? Oh, yeah, here it is right here. That's flux. Is equal to the integral of rho dv with a 1 over epsilon naught out in front. Now, I'm not going to prove this. This surface integral right here is not over an open surface like what we were doing here, but it is over a closed surface. The surface must be closed. It has to be closed in order for this to work. So to show that, what we do is we put a little loop over this, saying that the surface has no holes in it. Okay? The volume here is the volume that this surface contains. So for example, if I were to look at these closed surfaces right here, the volume of this would be the volume of a sphere. The surface would be this thing right here that holds the volume. Here, the volume would be the volume of a cube, but the surface would be the sides of the cube that hold the volume in. Okay? Now, so one question you might have here is, what's the big deal? Why is this useful? Why do we care about Gauss's law? And what Gauss's law does is to allow you to talk about the electric field that's due to charges, this is charge density, that sit within some area of space. The trick is to draw your surface around that area in such a way that it fits the symmetry of the charge that you're looking at. Now, so what do I mean? Well, let me show you a simple example. We'll start with, how about the electric field? What is the electric field due to a point charge? Now, we already know the answer to this. Okay, we already know what the answer is. We know that the electric field in magnitude, to be clear, is going to look something like 1 over 4 pi epsilon naught q over r squared. This is what it's going to look like. Now, when you add the potential that it might not be at the origin, that's when you have the r minus r prime stuff going on. We're going to assume that the charge here is sitting at the origin. So the r minus r prime stuff is just r. And we're also not looking at the vector property of it yet. We know, for example, that we know what the field already looks like. We know what direction it's going to point. It's going to be radially symmetric. It's going to point outwards from the charge because, we're going to assume that this is a positive charge. So, on the right-hand side, what you're doing is you're adding up all of the bits of charge that sit in your volume. So here, though, in this example, the bits of charge that we have are going to sit directly at the origin, and it's just 1. So, here's my charge Q that sits at the center. And what I want to do is to draw what we call a Gaussian surface. It's just a fake little surface that we draw that best embodies the symmetry of the electric field that we expect. So, in this case, and I'm going to dot it to sort of drill in the fact that this thing is fake. Let's see here. Let me make this a little bit more clear that it's what it is. Yeah, like this. There we go. So here's my fake little surface. And what I'm going to do is I'm going to center it on the charge like that. It is a closed surface, which means what I've drawn here really is a sphere. And to sort of show the fact that we're dealing with a sphere, let me add a little bit of substance to it. So there we go. It's a sphere. Looks like that. Okay. And this right here is the radius of my sphere, which I am going to call r. Now, I know from experience that for a point charge, the electric field is going to want to point outwards like this if it's a positive charge, and it's going to want to point inwards if it's a negative charge. But I also know, because of how it looks, that if I am r away, we'll say 1 meter away, that on the surface of that 1 meter in radius sphere, the magnitude of my electric field is constant. So if this is 1 meter, there's nothing else here that can change. And on that surface, I have a constant electric field. I also know that my surface itself has a surface normal that points out. And here, for a sphere, out is radially outwards. So what that means is the direction of my electric field as it points out is going to be in the same direction as my surface normal. Okay? So what I'd like to do is to use Gauss's law to show you that you do in fact get this result. Now, on the right-hand side, where you're basically adding up all the charges that you have in here, you only have one charge. So this adds up charges. Okay. And here I have one charge, so the value of this integral is just q. So I have, on the left-hand side, the integral over the closed surface, E dot n hat ds. And on the right-hand side, I have q over epsilon naught. Now, as I mentioned before, on this surface, the electric field, because it is parallel to the direction of out, the electric field on the surface is constant in magnitude. It's also parallel to n hat. So when I do E dot n hat, this is just E, the magnitude. But that's a constant, which means that on the left-hand side, I have an E that's constant there, so I can pull it out, and I'm integrating just the surface. And when you integrate the surface, all you're doing is asking the question, what's my surface area? What's the surface area of a sphere? Well, that's pretty easy. You can look that up. The surface area of the sphere here is 4 pi r squared. That's the equation for the area of a sphere. So what I have on the left-hand side is E times 4 pi r squared. On the right-hand side, I have q over epsilon naught. If I move all this stuff over here to the right-hand side, my electric field is q over 4 pi epsilon naught r squared. It's the same thing. Okay, so we were able to find, or at least verify, that this is in fact the electric field due to a point charge. Now, the power of Gauss's law comes from the fact that you are able to draw a surface many times that the electric field has a magnitude that's constant on the surface of, and that has a surface normal that happens to line up with the direction that the electric field is pointing, or against the direction, which would make it negative, which is fine. So to show you what you can do with this, here's an example that we've already done. We used vector calculus to do this. And here, the question I'm asking is, what is the electric field R above an infinite line of charge density lambda? Now, we know the relationship between charge density, charge, and length when it comes to this. You know, lambda itself is just Q over L. It's how much charge sits along a line. Now here, this thing is infinite. It goes from minus infinity to plus infinity. And it would be nonsensical to draw a shape that that embodied the whole length of charge, because it's just not possible. It would have an infinite surface area, and your integral wouldn't make any sense. But you can still use this. All you have to do is to acknowledge the fact that this equation is telling you about the electric field due to the charge that's on the inside and not on the outside. Here, what I would be dealing with would be, let's see, 1 over epsilon naught. Now, my charge lies along a line, if you want to think of it like that. Okay? Now, so the shape that best embodies the electric field that I expect is going to be a cylinder. Now, why is that? Well, if you remember when we integrated this result, one of the things we discovered was that at any given distance above, basically, if you look at the electric field due to a bit over here, there's going to be a companion bit over here that has an electric field that points this way. And at those points, the magnitudes of our electric fields will be the same. The directions will be sort of, in completely opposite directions like this. And our side-to-side parts cancel out, and that just gives us an up part. So what that means is that, I expect an electric field that, if I were to look at it, would sort of sweep radially around, pointing outwards, from my line of charge, pointing out like this, towards us, if you will, and away from us into the work area. So that said, let me just sort of clean this up a little bit. There. So that said, what I'm going to do is to draw my fake little surface here. And I'm going to capture some of this. So that would be about here, I think. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. And then let's make it here. So this is my fake little surface that I'm drawing here. It's going to look like this. I'll move this over there just to make it look better. There. Like that. So that's my cylinder, right? So my cylinder here has got a length, which I'm going to call L. And it has a radius, which I'm going to call R. Okay. Now there are 3 parts to a surface that's a cylinder. You have one end cap here, you have another end cap here, and then you have the area of the barrel here. Okay. Now let's talk about the direction of out. Now along my barrel, the direction of out is like this. Coming out of the screen towards us like this, following this curve, going into the screen over here. Now, the direction of my expected electric field is going to be in the same direction. So here, I'm going to call this n hat sub 3 because it's the third part, it's the barrel. My electric field, like I said, at the end of the day, I expect the side-to-side parts to sort of add out. And you're just going to be left with parts that point radially around this. Okay, so what you have here is on the barrel that E is constant because this thing has a distance of R. We expect the value of the electric field here to be the same as the value here. It's just the direction that would change since you're equal distances away. Coming out R away, we expect the value of the electric field to be the same. And so what that means here is that our electric field on the barrel of this is going to be constant, which is good. Now look on the end caps. On the end caps, you have electric field again that points up like this, the same direction as it does over here. But the direction of out is this way. This is the directions of n hat, this is E, this is the direction of n hat, and this is E. Now this is a problem. But it's a good problem for us because what that means is that when you look at the flux here on the edges, none of this field makes its way through. So if I were to take this closed surface here, this integral, and break it up into three parts, you'd have an integral of the electric field dot n hat ds over the first part right here. Then you have another part, E dot n hat ds over the second part right here. And then a third part, E dot n hat ds over our third area right here. These are 0. And the 0 because E dot n hat on each of the end caps is 0. And that's because when you do your dot product, you have a cosine of your angle, and cosine of 90 degrees is 0. So they don't contribute to the overall value of the flux because none of the field is making its way through the end caps. It's only riding along the sides. So it's this one right here that matters to us. And as I pointed out over here, on the surface of our barrel right here, of our cylinder, the magnitude of the electric field is constant. And it's also parallel to the unit vector, or the surface normal at this point, which means the dot product here is 1, and this is constant, so I can bring it out. And really what we're doing is we're adding up whatever the surface area of the barrel of the cylinder is. So on the left-hand side, I can pull the E out. Like I said, it's constant. RDS is just that of the barrel of the cylinder, and we're going to get to what that is here in a moment. Now, what's going on the right-hand side? Well, on the right-hand side, what I'm doing is I'm adding up all of the charge that sits in this line right here. Gauss's law only applies to the charge that's on the inside of your surface. So, charge, looking at this equation right here, is the charge density times however long this is, lambda times L. So, this right here is lambda times L. Now, what about the surface of this barrel? Now, again, the end caps don't contribute. It's just the barrel of the cylinder. And the way you get the area of the barrel of the cylinder is to think about a circumference that's been stacked. So the circumference of a circle is 2 pi times r. But we're stacking it L high, L long. So the total area, which is basically just a bunch of stacked circumferences, would be 2 pi r times L. This is the value of the integral of ds on the left-hand side. So E times 2 pi RL on the left-hand side. On the right-hand side, I have 1 over epsilon naught lambda times L. The L's we see cancel. And my electric field is equal to lambda over 2 pi epsilon naught r. And if you go back and you look at the previous chapter and look at what we got for the magnetic field due to an infinite line of charge, I think it was Z or Y above, this is what we got. Okay, this is the magnitude of it. The direction, you would put a R hat here or rho hat or whatever it is you want to call that radial cylindrical distance out. I guess axial distance if you want to think of it like that. So we didn't have to whip out any vector calculus or any complicated stuff right here. All we did was to play games with symmetry and geometry, which again is the power of Gauss's law. Now, let's do another example. What is E inside and outside of a spherically distributed uniform charge density rho that has a radius of r? So here's my charge right here. We're going to do the outside part first because it's actually a relevant result. Let me draw a coordinate system here to here to here. This is Z, this is Y, This is x right there. And like I said, we're going to do the outside part first. So just to make my life easy, what I'm going to do is let me create another slide here. And before I get any further, let me copy this over there so I can do the inside part there. So there. So the outside part first. And with the outside part, what I'm going to do is I'm going to draw a sphere that sits on the outside of the sphere of charge, because that fits the symmetry of what I'm looking at. So again, excuse me, I'll use a big old sphere like this. This is my big fake sphere. Centered like that. Okay. This is the direction of out. That's R. Now, my charge itself, that has a radius of big R. It's uniform, smoothly distributed through it. It's constant. Now, let's write down our Gauss's law. Gauss's law looks like this. E dot n hat ds is equal to 1 over epsilon naught rho dv. Now, let's talk about the left-hand side first. The left-hand side, if you look, this is the direction of out for my surface. Okay? So this is the direction of n hat. But this is also, if you look at it, a uniformly distributed sphere of charge. So I would expect the electric field to look a lot like the electric field due to a point charge. It would point radially outwards as well. So not only is this the direction of out, but this is also the direction of the electric field. It also would make sense that on a surface centered on the center of my charge distribution here, that the electric field on the surface is constant in magnitude. Okay? Spherically symmetric distribution of charge, spherical surface centered on that. The electric field in magnitude is going to be the same at all points on the surface that I drew. So what that means here is that E dot n hat, again, is just the magnitude of E, and the magnitude of E is constant. I can pull that out. So I'm stuck integrating over a closed surface, the integral ds, which we know what this is. This right here, we know is going to be, 4 times pi times the radius here, r squared. So what about here on the right-hand side? I have 1 over epsilon naught. I have rho, which is a constant. Okay. And I'm integrating the volume, dV. Well, what's the volume here? Well, the volume of a sphere, and again, I want to be very clear, the volume that I'm integrating here is where the charge lives. Okay? This is where the charge lives. So when I add up all of the charge that you have here, that charge sits in a volume that has that is 4/3 pi times big R cubed. Okay? Now, let's think about this. I'm adding up all of the charge that sits around here. Charge density is the charge that sits in a volume, which means when I take this and multiply it by this, really what that's doing is that's giving me big Q, which is the total charge that I have. So if I were to think of it like that, on the left-hand side, I have 4 pi r squared. On the right-hand side, I have Q over epsilon naught. If I move this over to the right-hand side, the electric field due to my big sphere of charge is Q over 4 pi epsilon. This looks familiar for some reason. I wonder why. Oh, it's the same electric field due to a point charge. And sure enough, when you deal with a big, spherically symmetric, uniform distribution of charge on the outside, it looks identical to that of a point charge. It looks the same. Now, what about on the inside, though? On the inside is a little more complicated. Okay, not too much more complicated, but just a little more complicated. So let me draw again a little circle here, or a sphere rather, and I'm going to center this sphere again on the very center of my distribution of charge, like this. But now, when I look at how much charge is on the inside, I'm not capturing all of the charge. I'm just capturing whatever is defined by the radius of my shape that I drew. I'm going to call this radius, again, lowercase r. Whoops. Yeah. Lowercase r. There. That looks better. Now, so on the left-hand side, the integral over a closed surface, E dot n hat ds. On the right-hand side, 1 over epsilon naught, the integral of rho dv. This is over a surface. This is over a volume. Now, let's talk about the left-hand side first. On the left-hand side, again, we're only able to talk about the charge on the inside. Gauss's law does not give you any information about the electric field on the outside, just on the inside. This right here, though, is the direction of the electric field we would expect due to the charge on the inside, kind of like that. And this is also the direction of the surface normal. N and E point in the same direction. The dot product just gives you E. Now, on the surface of this thing right here, we would expect, again, the magnitude of the electric field to be constant. So you can pull it out, and now you're just looking at whatever that area of that surface that I drew is, which again is 4 pi times r squared. Now, what about the right-hand side? The right-hand side is a little different. I'm going to pull my rho out. It's constant, after all. And now what I'm doing is I'm integrating dv. Well, that's the volume of the charge that's on the inside. And the volume of the charge that's on the inside is going to be 4/3 pi little r cubed. Why is it little r? Well, I'm not capturing all the charge. I'm just capturing the charge that's defined by the little bit that I have. So just like this got all of it, and I can call that big Q. Here, I'm not getting all of big Q. I'm just getting whatever this is right here. Okay. Now, so what I can do here is to equate these. 4 pi r squared on the left-hand side. On the right-hand side, I have rho over epsilon naught, 4/3 pi r cubed. 4 pi's go. There's 2 of these here. There's 3 of these. I'm going to get rid of all but one of those. And now my electric field is going to look like rho r over 3 epsilon naught. Okay? Now, you could conceivably do this using vector calculus. Really, quite honestly, there's no conceivable about it. You can absolutely do it. But the math is absolutely atrocious. It's horrendous because you can't work in Cartesian coordinates. You can't work in, circular polar coordinates. You can't work in cylindrical coordinates. You have to use spherical coordinates. And spherical coordinates for that is very complicated. Okay? But here, we were able to get this answer very easily by using Gauss's law. Now, that's one of the powers of Gauss's law, but you need to be warned about its use. You can't use it everywhere. It's really only suitable for areas in which you have some sort of symmetry that you can exploit. Here, our charge is distributed like a sphere. I can very easily find out, using spherical symmetry, what's going on there. Here, it looks like it's a line. The electric field looks like it's going to be on a cylinder. I can exploit that to find out what the electric field looks like. The minute you move away from simple shapes that have simple symmetry, Gauss's law becomes incredibly painful to use, and many times, more often than not, quite honestly, you're better off just doing the vector calculus. So that's it for our first video for this chapter. In the next video for this chapter, what we're going to do is we're going to discuss some of the implications of Gauss's law, specifically dealing with conductors. And I'll see you then.